I'm excited to make this video about multiplication. Basically, what I want to show is that quite a bit of higher level math, quite a bit of calculus is just extending our understanding of multiplication. So first of all, let's say what is multiplication. And so if we have a times b, I'm going to use the dot symbol for scalar multiplication just because I happen to like that symbol, is equal to, there are a couple of different ways to think about this conceptually as a scalar. One way is, let's say A represents 2 blocks. Then A times B represents the 2 blocks that many times. So let's say B represents 4. So we take the 2 blocks and we make 4 of those sets or pairs. 4. So with concrete numbers, we see that 2 times 4 is 1, 2, 3, 4, 5, 6, 7, 8. So that is one representation of scalar multiplication, and we're going to use that later when we talk about sums. Another representation is the idea of area. So I could just draw a rectangle, but I will draw a rectangle on a Cartesian plane. So let's say that A represents the length of our rectangle, and B represents the height of our rectangle. B. So then we know that A times B is represented by the area of this rectangle. So that is another representation of multiplication. We're also going to use that when we talk about integration and sums. And then the next one that I need to mention is the idea of stretching. So if we imagine a number line, okay, so we have this number line. We'll say this is 0, 1, 2, 3, 4, and I'll use different colors here. So let's say the A represents the number 2, and B represents the number 3, which means I need more lines here. So 5, 6. So then C, or the answer to A times B, would be this. So we take 2 and we multiply it by 3, it would be 6. And so more or less, it's a little harder to conceptually wrap your mind around what's going on here, but we stretched one by the value of the other. That's going to be really key when we talk about the dot product. So these are 3 ways to understand multiplication, just scalar, regular multiplication. And now we're going to take those and extend those to higher level math. So first we're going to say that, let's say if we have a vector, and so first of all, what is a vector? A vector is like a short little line segment. It has a direction, so it has a starting point and ending point, and it has a length. And as long as the direction and length are the same, then the vectors are considered the same. So these are the same. It doesn't matter actually where they are in space, just as long as they're pointing in the same direction, and the length is the same. Anyway, so that's short enough. That's kind of what, in general, what a vector is. So we can multiply these little boogers, and so there's 2 ways to do that. One is called the dot product. So here, and this, when you put a little line over it, it means it's a vector and not a scalar. So if we have A dot B, and here this means dot product, you can't just put them beside each other like you can with scalar multiplication. You can write this as This means A times B. This means A times B. This means A times B. And sometimes we do in parentheses. This means A times B. So there's many ways to write it in scalar, and it all means the same thing. That's not true with vectors. This means something very specific, A dot B. But it is in a sense a multiplication. And so conceptually, this one's a little bit challenging. But basically, so I'm going to draw a Cartesian plane to try to help get this a little more clear. And the idea is, so I had two vectors in mind. So let's say we take the vector 1, 1. So it starts at the origin, and it goes to 1, 1. And I should probably use colors here. And then let's take another vector. Yellow. These are really close colors. Oh, whatever. So let's say the next one is going to be, I don't want to use a close color, let's use blue. So the next one is going to be 0, 3. So I'd say that's roughly 0, 3. So what does it mean to take the dot product of these two vectors? Well, the idea is it has to do with the magnitude and the length. So if you're familiar with the process, which I'm not going to go over the process, but basically we have the vector 1, 1 dot vector 0, 3. Solution here, if you do the process, is 3. Another way to do this is to say that the magnitude of A, which this is A, times the magnitude of B, that's a regular multiplication because when you do the magnitude it becomes a scalar, times the cosine of the angle between them, and in this case it would be square root of 2 times 3, wait, should be, yeah, square root of 2 times 3 times 1 over square root of 2, because this is the angle 45 degrees. I set that up on purpose to make it easier. This also equals 3. So what we see then is, just very loosely, it has to do with if you're multiplying the magnitudes, but then also taking into consideration the angle between them. And so that's what's going on. And to try to explain it a little more fully, we need the stretching concept again. So if we take, you can go either way. I'm going to take A here and you form a right angle with B that goes up to the tip of A. So this is our new little vector. There's probably a name for it. I can't think of what it would be. So like little tiny a. And now what we do is we take this little tiny a and we just do the stretching thing like we did above. And when we stretch them out, well, in this case, we happen to get 3, which the length of this original one is 3. So the solution is actually the same as the magnitude of b in this case, but that's what you're doing. You're putting the one onto the other, and then you're stretching it out by the other one, just like we did up here. And it's conceptually, I realize it's a little muddy, but that's about the best I can do in a short little video. So that's the concept of a dot b. Now there's another way to multiply vectors, and this one, the algorithm for solving the multiplication is longer and more difficult, but conceptually that's easier to understand. So let's say we have these two vectors, and in this case I'm going to do our 3D plane. So we have A cross B, and so in this case we have the 3D plane. So that this would be X, Y, Z. So let's say that A extends like this in the XY plane. And let's say that B extends like this in the XY plane. So what you can do then is you can multiply these and the solution here, so I'm gonna have to label those so that I get this right, because this time order matters. With dot product, order doesn't matter. With cross product, order does actually matter. So this is A cross B. So what happens is you form 90-degree angles with both of these, which in this case, because they're both smoothly in the XY plane, that means it's jutting out into the Z plane. And it'll be either jutting straight up or straight down. And then you use the right-hand rule to figure out which direction it's shooting off in. So it's, let's see, A cross B, it should be up. So, oops. So it's pointing in this upward direction. And the it's supposed to be a right angle symbol. It forms right angles with each of these other vectors. So then, now the magnitude of it though is formed by the area that you would have by this parallelogram. So if you turn these into a parallelogram, this area is what is the magnitude of this cross product. So that's another form of multiplication. Another one is so I didn't actually spell it out. Let's use yellow now. Spell it out up here, but this is kind of also multiplication as an extension of addition, because here we're adding values, but we're using multiplication to tell us what to add and how many to add. And so in the same way, we combine this concept of adding and this concept of area under the curve to get this next type of multiplication. And this is going to be integration. And so let's start with this concept of area, right? So A times B, it's telling us actually the area of this shape that's formed. Well, if we take this shape and make it a little less predictable, easy to work with, say it has some shape like this, and we still want to think of multiplication as the area under the curve, what type of multiplication, it's not really the proper way to say it, but I think conceptually, pedagogically, I think it's helpful. So the multiplication that would get you this, and let's say here I have A, so let's say this is A1, say this is A2, so that means A2 minus A1 is this length. And let's say that this height here is B, which we'll also call B f of A. It's going to be helpful to recognize both of those. So if this was the xy plane, y would be f of x. This would be x1, x2. That's what's going on there with the naming. So we can say that this is equal to the integral from a1 to a2, oops, a2, a1 of f of a dA. We can also, it means the exact same thing to write it this way, integral from a1 to a2 of b dA. So I wrote it both ways because this is a little more clear for an understanding of like normally how integrals are written out, but this is the same thing, and this makes it a little more clear how that this is actually multiplication. So what you're doing is the a's over here and this dA here basically end up representing this length, and just it's more or less what's happening, and we're multiplying that by this b. And so that's how this is a multiplication. And if you know how to solve these, you realize that that muddied the waters on how to actually solve this. But conceptually, it's the same. And so when you apply these, especially in physics problems, you can use this form of multiplication. Actually, anytime you want, even when you could use this form of multiplication, but you have to use this when the top is not flat like it is here. So that's multiplication. And then this typically is taught from the idea of sums, and sums are taking this idea as addition, which we see up here that multiplication is an extension of addition, so I think it's worth mentioning. So the idea here is that you take the pink. So if we take the sum from I equals 1 to n of f of x sub I. I have to look at my paper because I almost never use this sum notation. D delta x. So what happens here is we're adding, right? And this sum turns into this. So it's another way that this is like multiplication, because if we take this and we instead say that the limit as n approaches infinity, it's hard to read, of the sum from I equals 1 to n f of x sub I with a little star there, delta x. So this now, so what's happening in these instances is in the first one here, if we take this and we break it up into these little slices and kind of roughly sketch in, imagine that's a slice, that's a slice. Ideally, they need to be touching one another, but for graphically, I'm putting a space between them, but you would break up the whole thing into tiny little slices with no spaces. So if you have these little slices, delta x is, I should have actually wrote to keep the naming the same, this would be delta A. So it's the width of the rectangles. And this f of x would be b, or the height of the rectangles. But in this case, they're actually flat. They're actually real rectangles. And you're just multiplying the width times the height. And so that's multiplication to find the area, just like here. But then what you're doing is you're adding all of the little pieces together. And that's like this right here. And so that's what this tells us. This is actually equal to, so this is not exactly equal to integration. It's the core concept behind it. When you take the limit as n approaches infinity, now this is equal to integration. And we'll just say f of a, I should use x, f of x dx. I'm not going to write everything there. So now the idea is just that you take the slices and make them as thin as you can imagine. But yeah, but otherwise you still do the same thing. So anyway, roughly, that's how integration relates to a multiplication. And now, all right, so now let's take this and extend this to 3D space. Now we're entering the territory of Calc 3. Let's use this color. So, right, so for this one, we're going to have to extend a regular concept of multiplication to 3 numbers instead of just 2. So let's say we have A times B times C. So conceptually, we can think of that as the volume under a, life of me, I can't think of the proper name. It's not actually a cube, it would be a rectangle, prism maybe? I can't remember the word for it. Anyway, it's this 3D shape. Oops. So we have this shape, right? And let's say that A is this line, B is this line, C is this line. Well then, the multiplication of all 3 of these together is the volume of this shape. So conceptually, that's what's going on. And that's important for 2 more things I want to touch on briefly here. So let's say we have this next one, we're going to call it the double integral. And we'll go B1 to B2. think we did A1 to A2. And we'll call this C, DA, DB. And so this is basically the same. It's like as if we're multiplying C times A times B, just like over here, and kind of compare it with up there. And this is equal to, conceptually, so the same idea, we have some value for A, and we have some value for B. And in this case, the way I have it set up right now, they need to be straight lines. So we have this, and this would just be an area if it was just A times B. But then we multiply it by some value C. And just like here, the value that we kept kind of regular could be like a funky shape. Here, we're doing the same thing. So use a different color here. So we're extending this up into the z-axis. So just like before over here, this is multiplication. This form of multiplication now tells you the volume under this curve. And like I said, this is not actually multiplication, but it's helpful conceptually to think of it that way because you will often apply this in a place where you might expect to apply multiplication. The last one that I want to touch on is conceptually very difficult to explain. It's not going to be clear, I don't think, in this uh, short little time that I have left. It's flux is what it is. So if you, Khan Academy has a very excellent video where he describes conceptually what flux represents, but I'm not going to take the time to make it really nice here. But basically, if we have this surface integral of f is a vector, dot ds, we're doing dot product, and s is also a vector, but s here is a special kind of vector. And so we have some surface, and so this is equal to, so how to consider, I want to use the idea of a sphere. So let's say we have a sphere. And I'm going to borrow some ideas from Khan Academy's video because it was a really good explanation, honestly. I'd definitely go check it out. And but what happens is the S here represents the normal vectors to the surface. So surface here is like the skin of a 3D shape. So this is a sphere in 3D space, and so the surface is like the skin, the outer layer, of it, right? It's not the whole volume, like it's not a solid, it's just the surface. And in this case, so if we take a tiny little piece of that surface out just for imagination purposes, so this is a little patch of the sphere. And the normal vector is a vector that is perpendicular to your tiny little patch. So you can kind of imagine that's perpendicular. And also it just so happens that it has to have a magnitude of 1. And there would be these little, use a different color, there would be these little normal vectors everywhere. So, you know, at whatever angle around it, there'll be all these little normal vectors, some extending out towards the camera, and so on, all around the whole thing. Then um, F here is a vector field. And so I'm not going to draw the whole field because it's going to get really, really messy. But let's say if we take F as a little vector right here. So it may not point in exactly the same direction as the normal vector. That's the key. And I'm going to change the color of that normal vector because it's really hard to see. So this is our normal vector. So that's what this represents, the normal vector. It's supposed to be perpendicular to the surface. I kind of accidentally drew it at an angle there, but and then the red is representing the vector field. And so just like we had the dot product multiplication over here, where it's kind of like this like lining them up and then stretching them. you line up one with the other and then stretch it. That's basically the same exact thing that's happening here. You, let's say that we were to, I'm going to do the purple onto the red because mathematically it's the same, even though conceptually it would be the red onto the purple. But because I drew this one longer, I think visually it'll look a little better this way. So first it's really hard to see. All right, so we take the one and we put it onto the other. Then we stretch that one by the length of the other one. We'll just kind of right over top of that. So this, stretch it by the length of the other. So I just made up that length. I don't know if that was the proper length for the answer, but you get the idea. It's basically like this stretching concept, the concept from dot product. We're doing that, and we would do it throughout the entire surface. For every place there is a normal vector on this surface, which is essentially everywhere, and we're seeing how much of the uh, vector field lines up with the surface, the normal to the surface. So yeah, so there's a whole bunch of how multiplication is really not quite so simple, because when you end up doing multiplication in physics, you frequently have to, depending on how you study and how you learn, but if you want to imagine, force equals mass times acceleration, then you're going to say, well, yeah, that's true, except when we have to apply some other form of multiplication to this formula. And so that's why I think it's fair to say that these are extensions of multiplication.